radio observatories. And here you see a map of Alaska, and for scale, it's about 1,000 kilometers from down here in the southern part of the state all the way up to the tip of the northern part of the state. So it's quite large. And Anchorage is right down here in what we call South Central Alaska. And I established that observatory in 2008. And then in 2015, I built one down in the area called Kenai Peninsula. And that was a remotely controlled operation. And then in 2019, I was invited up to HARP, and I've built an observatory up there, and that's also remotely controlled. So what I do is I'm a part of the eCallisto Solar Radio Spectrometer Network, and I have 3 installations here in Alaska that contribute data to that. I also work a lot with the long wavelength array. In fact, I sell the antenna and accessories for it and participate in that project. I do a Jupiter radio at about 20 megahertz in the HF band, and doing that depends a lot on RFI, which is a chronic problem just about everywhere, including where I live. And so my main interests are really the radio science and radio propagation, things like solar flare effects on propagation. I also do meteor trail and aurora radio reflections using WWV and WWVH time frequency stations. And so really what I have is a bistatic radar, and the transmitters are at the stations in Colorado and Hawaii, and then the receiver is here in Anchorage. And then I record the reflections off of meteor trails and aurora radio reflections, and I'll show some of that, some of the aurora work that I did here a little bit later. And of course, the last thing is the geomagnetic part of it, using the SAM-3, and I've been doing that since about 2008 as well. And I also sell the SAM-3 kits worldwide now. I started out doing it at the request of the designers, just for the United States and everywhere basically but Europe. But here a few years ago, they asked me to take over the whole thing. So I do it worldwide now. And I ship those kits to everywhere, Pakistan, Australia, even the United States. So let's talk now about geomagnetism, which is the study of Earth's magnetic environment. And the first scientific study of that was done by William Gilbert, and he published a book, The Magnet, in 1600. And it was translated into English in, I believe, the mid-1800s. And you can still buy copies of that book. Of course, they're the translated version, and it's quite interesting reading. It's even though it's written in English, it's written in 1850s English, and so it's a challenge getting through that, but it's still quite a readable book. Magnetism has been used for compass navigation for quite some time. I don't think anybody really knows how long, but I would say probably at least 1,000 years, maybe more, maybe 2,000 years. One thing that's really important to understand is that the origin of Earth's magnetic field is still far from complete. Even though it's been studied scientifically since the 1600s, we still are far from knowing how things work. So let's look at some of the basic characteristics of magnetism. Well, we know that the magnetism results from motions of electric charges rotations in their orbits, spins about their axis, and so on. That's kind of at the fundamental level. And then when you add those individual atoms up, then we have varying amplitudes of magnetic fields. So since we have electric currents, we then have automatically produce magnetic fields. And one of the fundamental parts of magnetism is the magnetic dipole. And so the magnetic dipole can be represented by a bar magnet, which is a pretty good dipole. And we've all done the experiment in school, and I used to do this at home as well, with a bar magnet, and then you sprinkle metal filings around it, put the magnet underneath a piece of paper, and then sprinkle some metal filings. And you get, you see that the metal filings line up with the magnetic field lines. And so that's a really interesting experiment. I'm going to turn on my spotlight here. So you can see the magnetic field lines here, and they pretty well follow just exactly what we've shown theoretically over on the left. Now I can't get my slides to advance here. Let me keep trying. There we go. The magnetic field at the Earth's surface is very similar to the field produced by a magnetic dipole. And the way this was discovered was measurements were taken all over the world of the vector, the magnetic field vector, and they were plotted on a piece of paper, and someone said, wow, that looks just like we have a magnetic dipole or a bar magnet in the center of the Earth. And we don't really have a bar magnet there, but the field that's at the surface of the Earth looks like we do. The field is tilted around 23 degrees or so, and that changes slowly over time. And it's also not centered in the center of the Earth. If you look very closely at the magnetic field lines, you find that this so-called dipole is actually offset, I think, a couple of 100 kilometers from the center of the Earth. So we have the two different poles at the north and south of the Earth. We have a geographic North Pole, which is, marks the spin axis of the Earth. And then we have the magnetic North Pole, which marks where this dipole field converges at the top and bottom of the world. And in this representation shown here, you can see that they're quite some distance apart. Now this magnetic North Pole wanders around up here in the northern part of the world and in the southern part of the world, and changes very slowly over time. And I'll show you some slides on that here in a minute. Now, one of the things that has puzzled people for a very long time is that what is the Earth's, where does this magnetic field come from? Well, it is thought that there is a solid inner core in Earth, in the center of the Earth, that's it's solid due to the high pressure from gravity, and it's thought to be pure iron. And then we have this liquid outer core here around the solid core, and they are thought to slowly rotate around each other. And these thoughts have come about by a lot of measurements that have been made, seismic measurements and so on. And it looks like maybe this is actually a pretty good model. And the exact mechanism, though, for the production of the field is not known, in spite of a lot of claims that it is known. But there is one idea that is pretty good, and that uses the concept of convection, heat flow in the outer core, that when you have a a movement of current, then you have a generation of a magnetic field. So this is a pretty popular concept, and a lot of people agree with it, but unfortunately it doesn't explain everything that's observed. And of course we know that if we have a measurement and our theory doesn't comply with the measurement, then what do? We say the measurement is wrong, right? Well, not really. We know that our theory needs some tweaking or some adjustment. So when you read scientific papers on geomagnetism, then there are certain trigger words that you need to look for. When a scientist says something is certain about the magnetic field, what that really means is that it's dubious. If he says undoubtedly it's undoubtedly a solid iron core, well, maybe it is, maybe not. We have positive proof of this thing, and really what it is a vague suggestion, and so on. So, oh yes, and we have a pure iron core. Well, it's an uncertain mixture of all elements. And Francis Birch is the person that did this translation for us, so we're indebted to him to straighten this out. Now let's look a little bit more at the magnetic environment. The Earth's magnetic field forms a volume called the magnetosphere in the surrounding space. And this is just an artist's representation of that, with the sun out here on the upper right-hand corner. And then these wispy lines are the magnetic field. We have what's called the magnetosphere, and if you look at the Earth, which is right here, this small little dot right here in the middle of this image, the Earth's magnetic field, or its magnetosphere, stretches out about 8 to 10 Earth radii on the sunward or daylight side, and then is stretched out hundreds of Earth radii on the tailward or downwind night side of the magnetic field. And we have the solar wind and the magnetic field that's frozen into the solar wind, and we have a bow shock from the solar wind, and it's so in general we have the solar wind is blocked from blowing directly on Earth by this magnetosphere. Now the shape of the magnetosphere is determined by the solar wind, and if we didn't have a solar wind, we'd have a simple dipole field. And so let's look at this animation here. There's a simple dipole field, and with the wind blowing on it though, you see that it gets compressed on the sunward side and then stretched out here on the downwind side. And again, this is maybe 8 to 10 Earth radii distance on this side, and hundreds of radii going out on the other night side. There are really two components to Earth's magnetic field. There's the internal field, or the main field, and that's generated within Earth itself, and that represents about 90% of what we measure and observe on Earth's surface. And then we also have about roughly a 10%, which are magnetic components which are entirely controlled by the sun. That external field includes things like remnant magnetism. Those are ore bodies or rocks that were magnetized somehow a long time ago maybe, and it's just still there. We have magnetic fields that are embedded in the solar wind, and these fields are frozen into the solar wind and flow with it. So the sun's magnetic field then stretches out into space and is stretched out by the solar wind. We also have magnetic fields that are generated by ring currents that flow around the Earth. We have this equatorial electrojet, which is a current system that flows roughly over the equator around Earth, and it's pretty much fixed in space, and then the Earth rotates below it, and it's generated by the sun. And then we have the auroral electrojet, which is at higher latitudes. In fact, I'm on a good day, I'm right below it here in Anchorage. And this is generated by a lot of different things, field line currents that are coming in through Earth's magnetic field. And again, these are relatively fixed in space while the Earth rotates underneath them. We also have anomalous fields, and here's a map or a copy of a portion of a map for the Aleutian Islands, which is the island chain that stretches out south and west of Alaska. And you notice there's a mark right down here. It says magnetic disturbances of as much as 6 degrees exist at ground level at this location here. So if you were sailing your boat by this area, your compass is not going to be reading very accurate in the vicinity of this cape right here in the Aleutian Islands. And this is just one of many that are down in that part of the world, and they're scattered. There are magnetic anomalies like this all around the world, some worse and some not so bad as shown here. So that's what we're looking at in terms of the magnetosphere and Earth's magnetic field. And to put things in perspective, I have this table here, and Earth's magnetic field, this is the magnetic induction or the flux density of the magnetic field, and right here in the middle is the Earth. And so this would be 1/10,000 Tesla, which is a unit of measure for magnetic flux density. And that equates to about in the neighborhood of maybe 50 to 60,000 nanoteslas. Nanotesla is a really convenient unit of measure when you're talking about the Earth. But then when you get out to the sun, we have a magnetic field that's about 100 times stronger. And if we go to the surface of neutron stars, then we've got, 10 billion times stronger magnetic fields compared to Earth. So Earth's field is fairly puny compared to even the sun, or even Jupiter for that matter. Your refrigerator magnet that everybody has stuck on their refrigerators is about 100 times stronger than Earth's magnetic field. And then going the other way, if we go out into the interstellar medium, so this is out in deep space, the field is in the neighborhood of about a nanotesla, or maybe a half a nanotesla. So we have magnetic fields in outer space, but they're pretty weak, but they do have an influence on what happens out there. The heart itself, the human heart generates a magnetic field 1/10 to the 11th. That's pretty weak. Even the brain has got a magnetic field associated with it. Now let's look at some time scales. The Earth's magnetic field spans really large time scales from femtoseconds, which is 10 to the 15th, 1/10 to the 15th seconds, and that's maybe due to sunlight. And then we also have at the other end of the scale, we have changes in the Earth's magnetic field that span millions or even billions of years. And this includes magnetic reversals of the Earth's magnetic field, which I have a little animation of that I'll show later. So over the short term, we have things that from a human perspective, we can actually measure. And we have whistlers, and I'll play a whistler for you here in a minute. Those are on the order of a millisecond or so time scale. We have micro pulsations in the Earth's magnetic field that span maybe up to a few hundred seconds. And I'll show you some measurements of that here later. We have the ring currents I mentioned, the equatorial and electrojet ring currents. And the solar rotation affects the Earth's magnetic field, particularly that's the part of the external part I mentioned earlier. That has a 20-day period, roughly. We have our solar sunspots, which have 11-year cycles. So we've spanned from a millisecond up to 11 years or so, and that gives us a pretty good human perspective on the time scales. Now here's a recording of a whistler. This is a phenomena that's related to lightning on Earth. So we have lightning shown over here on the left-hand side, and the lightning then produces an impulse, electromagnetic impulse that travels along Earth's magnetic field line, and it may actually go around and bounce back. And so when we detect that that impulse, it sounds like this. And hopefully you'll be able to hear this.
1996, hour 0, minute 16, whistlers.
So that was a whistler, and that was an excellent recording of whistlers. You can certainly do this at home safely, and but the ones I hear that are made by people like me that are really doing this from an amateur perspective, they're always much noisier and much weaker. Now, the Earth's magnetic field variations correspond to sun rotation period of about 27 days. And the sun rotates faster at the equator, and that was determined by measuring the sunspots. They found that sunspots moved quicker near the sun's equator than they did at higher latitudes. So that 27-day period then is kind of a nominal number. It's maybe faster at the equator, or I'm sorry, fastest at the equator and slower at higher latitudes. So anything that happens at higher latitudes that affects Earth's magnetic field, then it's going to be it's going to be longer than 27 days. The geomagnetic, a lot of geomagnetic activity that we measure on Earth's surface is related to sunspots, and these tend to recur with a 27-day period. So if we watch this animation or this movie here of the sunspots, then we'll notice that certain sunspots come around, disappear, and then come around 27 days later. So anything that we measure on Earth that's affected by the sun's sunspots then will operate on that same cycle. So we have this nominal 11-year cycle, some years slower, some years faster, and the sun's magnetic field reverses on a 20-year cycle. So we'll have 11 years of, say, a positive polarity, then it reverses, and then we have another 11 years, but it's at a negative polarity. And then that continues on forever. Now the Earth's magnetic field also varies quite slowly within the Earth, and these are called secular variations. So these are changes that take place in the magnetic field amplitude and direction as measured at any observatory. So over long periods of time, you'll see some the magnetic vector amplitude will change and its direction will change. Now this animation that you're seeing here spans several hundred years, and what this is showing is the declination. Now the declination is the angular difference between true north and magnetic north. And there's me in Alaska right there, and you can see that I don't see much change over the period of this animation. But other parts of the world, you can see there's quite a large change in the magnetic declination, as shown here. And just to put this in perspective, back in the 1960s, when I was learning to fly and learning to use aeronautical charts, the magnetic declination at that time was about 26 degrees east. That means the magnetic field pointed east of true north. And today, though, in 2021, it's closer to 15.5 degrees. So there's been a 10-degree change in the direction of the magnetic field when measured at Anchorage. And if you're using a map which is based on true north coordinates, then you need to know that in order to navigate. Now, occasionally, the magnetic field, the drift of the magnetic field changes suddenly. And by suddenly, we mean in less than 1 year. So, and these are called magnetic jerks. And if you look at a plot of the rate of change of the amplitude or direction, you'll notice that over at some period of time, they might rapidly change and change direction. And this plot here is courtesy of the British Geological Society, or I'm sorry, a British Geological Survey, and it shows a plot of the rate of change over from 1900 up to about 2010, so almost 100 years. And you can see there's been some fairly rapid changes in the direction there. So those are called magnetic jerks, and I haven't been observing long enough to see something like that, but if I live long enough, maybe I will. Now, another thing about Earth's magnetic field in terms of timescales is the Earth's dipole field reverses polarity at apparently random times. People have tried to say, well, it has an average period of maybe 100,000 years for the reversals within the last 25 million years. But the problem is that the range of years between reversals is so large that averages really don't mean much. Now this plot over here on the right-hand side shows magnetic reversals, the black being one polarity and the white being the opposite polarity. And this covers a span of about 80 million years. And you can see there's been quite a few changes over the last 80 million years or so. But the length of time at any given polarity has really, there's really nothing average about that. It's pretty hard to put a simple statistic on that, on reversals. Now I'm going to show you an animation that was done that shows the magnetic reversal. And what this is someone had modeled the Earth's core and then just let it run to see what would happen. And so if we do that, this is the surface of the Earth. So here's our North Pole here in blue, and red and orange is the South Pole. And so this is the surface up here on the upper part, and then below that is the inside of the outer core. So let's just run this simulation and see what happens. And I don't know what the time frame is for this, but I'm going to guess it's going to be, we're talking, millions of years. Now we've got a South Pole up at the northern part of the world. So, and that didn't take long for this simulation. But it shows you that people are really interested in seeing how this all works. And when they can make a simulation of the outer core and just let it run to see what happens, and then we can get a reversal, then that tells you that maybe we're on the right track with this model. So I'll let it run again here. You can see the South Pole flips, kind of comes back, and then it flips and stays there for a while. So that's an animation. Who knows if it's correct or not, but it sure is fun to look at. Now, another thing about the external field is that it varies on a daily basis. The variation isn't much. Maybe a few tens of nanotesla over a daily period. This is a plot that I made. This goes back to 2009, and I really don't know if the slow variation here is due to temperature changes affecting the sensor, or if this is actually a diurnal change in the Earth's magnetic field. And I kind of suspect it might be diurnal. Now we need to talk about geomagnetic disturbances. That's one of the key reasons that we are really so interested in the magnetic field, in Earth's magnetic field, is because disturbances can affect things that we do here on Earth. Now, a couple disturbances that we're really interested in, for example, are coronal mass ejections. And these are really huge explosions of matter, billions or trillions of tons of matter that are blown from the suns and hit the Earth's magnetosphere. Now, a coronal mass ejection is no big deal if it's not pointed at Earth. But if it is, then it's possible that we can have a major disturbance on Earth, and it could affect a lot of things. Now, one of the interesting things about a CME, or a coronal mass ejection, is that accompanying most CMEs are solar radio emissions. And these are called type 2 solar radio emissions. They are a slow sweep in frequency as the charged particles move away from the sun. The cloud density becomes less dense, and the radio emission frequency drops. So these are called slow sweep type 2 solar radio emissions. We also have a phenomenon called magnetic reconnection, and that's when the sun's magnetic field links directly with Earth's magnetic field, and this produces substorms or even magnetic storms on Earth. And we'll see some examples of that. So the CMEs, and there's another phenomenon called coronal hole high-speed streams. These can affect Earth's magnetic field as well. Now, this image on the left here is an image of the sun's disk is this white line here in the middle, and then we have this occulting disk so that we can observe things that are going on around the sun. And you can see a CME, or a coronal mass ejection, being blown away from the sun here on this image. Now, coronal hole high-speed streams, we can't see those except through real short wavelengths. And this image of the sun shows a coronal hole as a dark region, and it's a lower temperature region that shows up dark on these types of images. This is a quite large coronal hole that is being shown there. I'm starting to get a little hoarse. I have some animations that I'd like to show of coronal mass ejections. This is an animation made by NASA, and you can see the cloud's been launched away from the sun, and then it eventually intercepts Earth in this case, and the magnetic field looks like a dipole until it's struck. And then we have this activity in the northern part of the of Earth shown there. The magnetosphere gets stretched out, and then over here on the far right we see particles being drawn in, and those are drawn into Earth. And then let's continue on over here on the right and see what's going on. We have the cloud being blown from the sun. We see some magnetic reconnection. And then over here in the tail, we see another magnetic reconnection that basically convects charged particles over into the northern part of Earth. Now the contrast isn't too good here, but we can see some aurora at the north and south sides of the Earth. This is another anime, or this is actually a movie of a coronal mass ejection here on the left, and I'll play that. And you can see a flare taking place, and then all of this matter gets blown away from the sun. So that's quite really interesting to look at, I think, to see a huge amount of matter being blown away from the sun like that. And then we also have another animation made by NASA, or actually a movie made by NASA, and this covers about a 1-month time span. And I think you'll see quite a few coronal mass ejections being blown away from the sun. So this is really speeded up. We're covering about a day a second or so. There's somebody in their spacecraft going by. So that was back in 1998, and that movie is actually pretty tame, I think. I've got another one here that's not quite so tame. And what's interesting to watch about this one is that if you look at the stars in the background, these little white dots that you see, they're going to be moving left to right. But there's this guy in a spaceship that apparently didn't get the word, and he's going the wrong way on this one-way path. And this animation covers about 3 weeks back in 2003. So let's watch and see what happens here. There's some pretty good puffs coming off the sun. This is in October of 2003. And these explosions get more and more powerful as time goes on, until that one blows right toward the spacecraft that's making these images. And that's what all that pixelation that you see there is essentially overload of the sensors in the spacecraft. And the sun is this little white circle here in the middle. The occulting disk then blocks that out so that we can actually observe what's going on around here. So that's really an interesting movie, I think, because it shows those particles coming right at you and wiping out the imager on that spacecraft. Now, I mentioned magnetic reconnection as another phenomenon that affects Earth's magnetic field, and I've got another animation here that I'll show for that. Here we've got the solar wind. This bright orange line are the magnetic fields that are frozen into the solar wind, and you can see that they're hitting Earth's magnetic field in this area here, and then flowing around them, being split, so that Earth's magnetic field lines are normally closed around itself in a magnetosphere. But then when we get this reconnection, those magnetic field lines in the northern and southern parts of the Earth are actually open. And when they open, then stuff can flow in toward the north and south poles and be brought back into the magnetotail, where they're stored for maybe a little while, and then they convect back and produce aurora. So let's take another look at that animation. Our solar wind, its magnetic field from the sun, and then we have reconnection here on the sunward side, and you can see those formerly closed magnetic field lines then temporarily become open. Here's another animation of that process. There seems to be a lot of preamble on this one. Now we have Earth's magnetic field. And we had magnetic reconnection in the magnetotail. So not only do we have magnetic reconnection on the sunward side, but then maybe an hour or a few hours later that we have reconnection back in the magnetotail. And that's basically what that's doing, is closing up those open field lines. So we have open field lines here on the sunward side, and then they flow back down where they reconnect, and then that convects a lot of charged particles that rain down onto the northern part of the and southern part of the Earth, producing aurora. And that's called precipitation. Now the manifestation of that is visible and radio aurora, and I'll show an animation over here on the left that shows the aurora oval, and this is now produced. These bright areas you see here are where that precipitation takes place, and those electrons or charged particles that are coming back from the magnetotail on the night side are flowing down and interacting with the Earth's atmosphere. And then here's the visible aurora shown from the surface. and it's pretty spectacular. I used to be able to see that all the time in Anchorage pretty regularly, but light pollution the last 30 years or so, I don't think I've seen the aurora for maybe 30 years in Anchorage. Another manifestation of geomagnetic disturbances are radio propagation effects. And two of those are the radio and visible aurora. We've seen the visible aurora in the previous slides, but radio and visible aurora are two separate phenomena with the same basic origin. You don't necessarily have them together. Often you do, but it's not a requirement that if you have radio aurora, then you have visible aurora, or vice versa. So now radio aurora is due to enhanced ionization of the atmospheric gases by those precipitating electrons, and that causes reflection of radio waves when the radio frequency is below the plasma critical frequency at about 100 kilometer altitude or so. Now, visible aurora, on the other hand, is light emission through excitation of the gases. So the oxygen and nitrogen and so on that make up the Earth's atmosphere, the precipitating electrons then actually excite those gases and make them glow. And so maybe another name for visible aurora is air glow. Radio aurora is really interesting, especially for me, because I've been for the last several months been working on this pretty heavily. Increased ionization at about 100 kilometer altitude, maybe all the way up to 400 kilometers or so. And that causes radio reflections at the high frequency band all the way up to the UHF, maybe a few gigahertz. So the reflection mechanism at HF is probably due to reflection caused by the high electron density, where the plasma frequency is at a value above the frequency of the radio wave, so it reflects. Now, when you get to the higher, in the UHF and the VHF range, you need extremely high electron densities in order to reflect a radio wave. So the reflection mechanism for radio aurora at UHF is probably different. It's probably more like maybe coherent scattering or something like that. One of the confusing parts about discussions of radio aurora, are we talking about reflections or are we talking about emissions from the aurora itself? And I've never knowingly detected emissions from from aurora. It's my understanding that it's basically an increase in background noise level. So, and it's very weak. So in other words, you already have your background noise and it's enhanced by the by the aurora itself. And so that's a different phenomena from the reflections that we're probably most familiar with. I have an example of some aurora radio reflections that I observed here just back in February, just not too long ago. And over here on the lower left, is a magnetogram from my SAM-3. And what I've done is I've blown it up a little bit so that the vertical scale is enhanced. And here's a kind of a time stamp. This red arrow is a time stamp. It just so happens it was right at 0600 UTC that all three components of the magnetic field that I was measuring all of a sudden took a jump, a very, very quick, sharp jump. And simultaneously over here on this Argo chart, which is just a narrowband representation, a narrowband spectrogram of the demodulated audio from my receiver. And so this is 0600 UTC right here, where the yellow arrow is. And you can see all of a sudden I started getting demodulated audio where I had none before. Now, this Argo chart isn't showing the carrier. What it is showing is the demodulated carrier. I have the receiver set for about a 1 kilohertz above WWV at 15 megahertz. So I'm about 1 kilohertz above 15 megahertz, and I have it set to lower sideband mode so that if there's a signal coming in at 15 megahertz, it is demodulated as a 1 kilohertz tone. So what you're seeing here then is that 1 kilohertz tone. And so that's the start of it right at 0600. And this chart here is a 2-hour record of that event. Here's the 0600 timestamp over here on the left. And then I have 0630, 0700, and 0730. And you can see that propagation or the detection of this 15 megahertz carrier then lasted about almost 2 hours with some gaps in there. And if you go back and look, you'll see that there was some changes in the magnetic field over that same 2 hours time span that you might be able to correlate with those gaps. For example, this dip here right at the 1 hour mark from the start would maybe correspond with this gap shown here. So we have 30 minutes there, 30 minutes there, so we've got about an hour to that point right there. So this is a chart that you can, if you have a magnetometer and receiver and a beacon transmitter somewhere for a bistatic radar, then you can do this in the safety of your own home. So kids, yes, you can do this at home. Now another phenomenon are ionospheric storms. And these are disturbances caused by magnetic activity in the ionosphere. These can last for several days. They're caused by or manifested as additional currents in the ionosphere. You will measure these on the ground as geomagnetic disturbances. And what happens is there's a reduction in the daytime critical frequencies of the F2 layer, which affects radio propagation. And you also may have enhanced F layer or E layer propagation, or you may have radio blackout. So it depends, there's a lot of variables there, depends on the sunspot cycle, and but ionospheric storms are another manifestation of a geomagnetic disturbance. Now this animation here shows an ionospheric storm as measured by the total electron content. Over the left is a quiet ionosphere, and then the storm was introduced and shown over here on the right. And you can see that for any given time, the quiet is green and yellow, whereas the disturbed or ionospheric storm is shown as reddish orange. About 0900 or so is when this happened to occur. And what total electron content is it's the density or the electron count in a column from Earth's surface on out as far as the ionosphere goes. So this is a way to measure the density of the ionosphere. Another phenomenon that occurs that are traceable back to magnetic disturbances are polar cap absorption, PCA, and this happens at higher latitudes and causes radio blackouts on over the pole radio paths and high latitude radio paths. So it doesn't necessarily the radio path doesn't necessarily have to be over the pole. It just needs to be at high latitudes where it could be affected by polar cap absorption. So what this is equivalent to the D layer becoming extremely dense and absorbing any radio waves that are attempting to penetrate it to get to the upper layers for refraction and reflection. In these events, the PCA events can last from maybe a few hours to several days, and a major impediment to radio propagation at northern or higher latitudes. We also have ionospheric patches and blobs that can be traced back to magnetic disturbances, and these are areas generally at higher latitudes where we have really greatly increased or greatly decreased ionization. And these blobs and patches move really, really fast. And they were discovered by radar that was used for radio aurora research. Now let's take a look at some measurements that I've done here in Anchorage. Now, Anchorage is just at the southern edge of the auroral oval, and so my magnetic latitude here is about 62 degrees, and geographic latitude is about 61 degrees. And I have real-time data that I publish on my website, and you can go to reeve.com/sam, and from there you can get to a real-time chart that's like I'm shown here. Now this data is shown on a magnetogram, and this shows what a magnetogram is illustrating. Over here on the left-hand side we have a vertical scale that is the magnetic field amplitude measured in nanotesla. And then the horizontal scale is a 24-hour time scale in UTC, and you'll notice that the time scale is broken into 3-hour synoptic periods. And so these 3-hour periods are then used to calculate the K index, which is a magnetic field index. It shows if the magnetic field is quiet with a low K index or disturbed with a higher K index. And this particular magnetogram here is produced by the SAM3, and you can optionally show sensor labels, the BX, BY, and BZ components of a 3-axis magnetometer. We also have warning bars. You can set the threshold so that if we see within a 15 or 20 minute period a rapid change like shown here, then we can set a threshold so that a red bar shows up on the magnetogram. And this is used as a warning. If you're a radio amateur, then you might point your antenna north and try to do some VHF contacts as a result of this disturbance. So in other words, you're going to use radio aurora as a propagation mechanism. So that's what a magnetogram is. And here's an example. This one I think this is just a few months ago, and what's really unusual about this is that all three components shown here are all K0. So this is a magnetically quiet day, and at northern latitudes this is really, really unusual. So I've only seen this a few times in the 10 years or so that I've been running my magnetometer at Anchorage. So that's an example of a magnetically quiet day. And then on a disturbed day, you can see that we have maybe a little bit of variation, but then a rapid change in the Earth's magnetic field. And now remember, these are 3-hour synoptic periods here. So right here at 1200 UTC, we can see there's been some kind of a disturbance, geomagnetic storm. Here's a noisy day. This is pretty quiet out until we get to around 1500 UTC, and then we start seeing these noisy periods. And now these might be micro pulsations. They sure fit the definition of micro pulsations. But what's unusual about this is that if you compare this to, say, even this chart here, we don't see much noise. We see maybe rapid changes in the magnitude that are pretty significant. But here we're seeing very rapid changes, and maybe on the order of 5 to 10 nanotesla. So that's a noisy day, or a noisy period of that day. Here we're showing a geomagnetic storm. This is about 10 years ago, and this was caused by a coronal mass ejection from the sun on 10th October 2010. And you can see that things were not too disturbed up until this point right here, about almost 1000 UTC. And then things started to change rapidly, and were pretty much disturbed for several hours, and then settled down, at least the variations settled down until maybe 2100 or so, and then became quiet again. So that's an example of a storm about 10 years ago. Geomagnetic sudden impulses are when that CME shock wave hits the magnetosphere, it causes a pulse. And here's an example of one here. The pulses normally are not very great, maybe 10, maybe 20, maybe 5 nanoteslas or so. And you can see one here about 1830 in the afternoon, the UTC evening. You might say, well, this looks like an impulse over here. And yes, it does look like an impulse, but it doesn't meet the definition of a geomagnetic sudden impulse. So this was just something, probably a regular routine disturbance at the high latitude that I'm at. Co-rotating interaction regions. When the solar wind is blowing at some speed, and then a coronal hole forms, the wind is blowing at a higher speed. That higher speed wind catches up with the lower speed wind, and then these, where it catches up, is called a co-rotating interaction region, and that can lead to disturbances in the magnetic field. And we see a couple disturbances here, and this particular one was time-stamped by the Space Weather Prediction Center as this was the intersection time, about 1430 or so. And we can see a dip in the BY component when that happens, and the BX component as well. coronal hole high-speed streams are another source for disturbances, and they produce an increase in the solar wind. And when the coronal holes, the wind from the coronal holes intercepts Earth, it can jiggle things around pretty good. And we can see in this plot here where we had a really quiet day, it's a little bit of variation, and then the arrival of a coronal hole high-speed stream, and we see that the BX and BY components both took a dive right at that point in time. So the magnetic field that was frozen into the high-speed stream then had some effect on Earth's magnetic field. Now, one thing I need to point out about these magnetograms is that I'm not showing the absolute value of the magnetic vector. They show that I'm showing the three components, but I'm showing that the components that have been normalized at the beginning of the UTC day. The chart is zeroed out, and so what we see throughout the day is relative to midnight the night before. And the reason for doing that with the SAM3 is because the temperature variations are pretty hard to get rid of with the sensors. And so if you just let this thing go, as the sensor temperature changes, this would eventually go off the plot as it drifts. Now, my sensors are buried about 1 meter below the surface, and I don't see much daily variations. But other people aren't quite so lucky to have a setup like that, so they see daily variations that could go off the chart if we didn't zero it out at midnight the night before. Here's another coronal high-speed stream and CME that came in about the same time and caused a disturbance. So this is, again, this is back in, I believe, October of 2010. So this is an older chart. But we can see a relatively quiet period and then lots of activity caused by these two phenomena. Another thing that we can do with magnetic measurements is produce a Bartle's diagram. And this was named after a fellow back in the, I believe he came up with this idea back in the 1930s. And so what he did is he plotted the K index, which is a measure of the level of the disturbance or quietness of the magnetic field, and he plots that every day. And over time, he noticed that there was a 27-day reoccurrence of disturbances. And so that was one of the early indications that the sun, the rotation period of the sun is about 27 days. This particular Bartle's diagram here is produced by the SAM3 software. You have to manually do this. You take you start up the Bartle's diagram software and then load the data that you want into it, and it produces these charts. So now we're going to go into the very last section of my presentation, and we're going to talk about the SAM3 magnetometer. And I need to warn you that I sell this device, have been for about 10 years now. I ship them all over the world, but you can use it to build your own geomagnetic observatory. It costs a few $100, US bucks, and it's actually a quite sophisticated device. The hardware supports 3 axes. Usually these are set to point north-south, east-west, and then vertical. And our standard is to point them true north true east, and vertical. And included with the SAM is logging, charting, analysis software. So you get all of that as part of the deal. It's a wonderful instrument for both short-term and long-term observing. And it's called the SAM-3 now. It's actually a part of the Space Weather Underground project, SWUG, which is a student outreach project initially started by the University of New Hampshire over on the eastern part of the United States. And it's been adopted up at the University of Alaska in Fairbanks, which is north of Anchorage here, which is where I went to college and got my electrical engineering degree. So SAM stands for Simple Aurora Monitor. And it was originally designed for radio amateurs. And it recognizes the fact that you have enhanced VHF propagation coincident with the aurora. So this was a device that was measured the magnetic field and used that as a proxy for aurora. And the original instrument was a 1 or 2 axis device, and that was what you got. But in 2008, it was upgraded to a 3-axis, and so now it's called the SAM-3. And so it's really actually a quite popular instrument with geomagnetism enthusiasts. The hardware consists of 1, 2, or 3 flux gate sensors, and associated with those sensors is a main controller printed circuit board. So all the hardware and firmware is on that board. And then you have software that you run on a PC that you use for logging, charting, and analysis. And you can also get a power supply, a plug-in adapter power supply, an enclosure, serial adapters, and so on as part of that if you want them. So if you buy the kit, you get basically a pile of parts. And there's about 100 components there. All of the electronic components are through-hole type. There's no surface mount except for the keyboard switches. There's 4 keyboard control switches. They're large and really easy to solder, so it's usually not a problem for most people to build this kit. And then the software and documentation and so on comes on a USB drive. Now, I also do I kept getting people asking me, can I buy this thing already built? And initially I didn't do that, but then I caved in and decided, okay, I can build these up. And so what you get when you buy the partially built kit is you get the keyboard and controller have been fully assembled and tested with the live sensors here in my lab. The display, we modify the display printed circuit board a little bit. I do all that. And so you get pre-assembled electronic components and then all the software and documents and so on. This shows the main controller printed circuit board, and you have your microcontroller. It's a PIC, microchip PIC, and all your ancillary integrated circuits, your connections to your keyboard and display. You have a battery for the real-time clock. You have voltage regulators. This is for the digital electronics. And then you have individual little voltage regulators for each of the 3 sensors. So that's what it looks like when you have when you get the enclosure and build it up and put it together. I'm working on a different enclosure that's a little bit easier to put together. It'll be pre-cut, everything will be pre-cut and pre-drilled, and it'll be far easier to mount the components than in this original enclosure, which required you to do some plastic cutting. The display is a liquid crystal display, a 4x20, and it shows the X, Y, and Z components, the K index, as well as the time in real time. And this unit will operate standalone. In other words, you can set this up and it'll run. There's no internal storage, so it doesn't actually store data internally, but it gives you a real-time display of what's going on. And you can connect to it and get you can hook a meter to it to get the K index on an analog meter, or you can hook a buzzer to it and a relay will close when you get a preset threshold change in the magnetic field, so you can point your antenna north or whatever you want to do with it. Or you can hook this up to a computer through an EIA 232 interface using a standard DB9 type connector. So in standalone mode, you get this real-time display of the magnetic field, the K index, and the time. You can output to an analog meter that'll show 1, 2, 3, 4, 5 through 9 for the K index. No internal storage, but you can hook it to a serial data recorder if you want. And I've done this for some custom installations where you can take this out in the field, operate it from a battery, and then use this serial data recorder to store the data. And then you can bring that back and put it on your PC and analyze it using the software that's supplied. Or you can control the unit from a PC running the supplied software. And you get the magnetograms like I showed previously. You can set the data collection interval. I hear somebody talking. Was there a question? I guess not. You can set the data interval.
Lorenzo has got his microphone unmuted, and I think you can hear someone chatting. I don't know whether it's... Aha.
Okay. The sample rate can be adjusted, and I'll show you that in just a second. You can operate from a PC with or without logging. And from my point of view, I don't know why you'd be running it from a PC if you didn't want to actually log the data. So that's what the capabilities are. The data output from this device is actually quite usable. It's not a proprietary format. It's not a binary file. The data is brought out at a modest 9,600 bits per second. It's saved as an ASCII text file. It's a tabular file that shows the time with the X, Y, and Z labels. And you can then use that data either with the software or load it into a spreadsheet program to plot the data. The data output interval, or the sampling rate, can be adjusted from 1 second all the way up to 120 seconds. Now, 1 second sampling rate is actually quite fast for Earth's magnetic field, and it produces a lot of data. I mean, you get some big files out of this over time. So I usually run mine at a 10-second or a 1/10 hertz rate. And some people run it at a 1 minute or a 60-second rate. So you can adjust that to your own liking, and which kind of makes it a pretty versatile instrument. Now the flux gate sensors are supplied with it. These are active devices. They operate off of 5 volts, which are supplied by the main controller board, and their output is a PWM, or a pulse width modulated waveform, that's proportional to the magnetic flux density. And their range is plus or minus 50,000 nanotesla, which is a really good marriage with the magnitude of Earth's magnetic field at the surface. So these are pretty good sensors. They have a pretty good resolution. The only negative is that they're temperature sensitive. In fact, they're a pretty good thermometer. So you have to put these in a thermally controlled environment and limit the amount of temperature change. Now, this picture that I've shown here is the Speak FGM3 flux gate sensor. Now, Bill Speak died here a few years ago, and the company disappeared, and I haven't been able to get these, the Speak sensors, but I do get an equivalent sensor that looks almost identical to these from a company in Europe. Now, what I do is I mount these sensors in a monkey cage. And this is made of wood, all non-conductive, non-magnetic material. And the only reason I do this is to provide an air cushion around the sensor. Now, I've never observed this, but people have said that if you don't allow the flux gate sensor to dissipate heat, it'll go into thermal runaway. I've never ever observed that. I've tried to make it happen, but I could never make it happen. But I like to be a little on the cautious side, so I provide this air gap around it and make this out of wood, and then this slides down into plastic plumbing pipe for a fixture to hold them in a fixed position. So this is a drawing here that is included in the SAM manual that I made up. You'll have a Y sensor. That'll be pointed, say, this way, horizontally to the right. You'll have the X sensor that's pointed out of the page, and then you have the Z sensor at the bottom that is pointed vertically. And these are all held together with plastic pipe, and the wiring, the cabling is then brought up to the surface and then to your main controller. And I mentioned earlier that the best way to control the temperature is to bury the sensors in the ground. And if you go to my website, you'll find some papers that I've done, both from a theoretical and a practical point of view, on how deep that should go. And to eliminate daily variations, in most soils, if you get down to about a meter depth, then you're in pretty good shape to eliminate daily temperature variations on the sensors. Here's an image of the sensor that I have installed here in Anchorage, sitting on a sawhorse. And so it looks like it's maybe a couple meters long, maybe 1.75 meters or so. And this part here is buried underground, and then you have the pipe coming up to a junction box, and this is where my cables then, and I have them connectorized cables that connect there. Okay, well, so that's pretty much it. Here's some resources that you might be interested in. And I know you're not going to be able to copy these unless you take a screenshot. But if you want a copy of this presentation, just let me know, and or maybe let Paul know, and I can send him a copy of the presentation, and we'll go from there. And if you have any questions, I'm more than happy to take them now.
Thank you very much. Thank you very much, Whit. That was great. One thing about magnetometry presentations, you get to use some fantastic videos and animations. Are there any questions? We've got time for maybe one or possibly two. I want to press on. Otherwise, if you think of something, stick it in the chat and we can come back to you later. Is there any question? If you want to hit the reaction button, raised hand, then you'll rise to the, you'll be promoted to the top of my screen.
Okay, I'm going to stop sharing now, Paul, and so I can see that chat.
Yes. Okay, do put your questions in the chat. I want to hand over to Wolfgang, and I make no apologies for those of you that were at the EUCARA meeting last Saturday, because some of this will be repeated, but it is worth repeating. So, Wolfgang, our screens are yours.
Well, thanks very much. I hope you can hear me.
Yes.
And let me share my screen, which is hopefully coming up.
Yes, that works.
Okay, let me just put this in full screen. Somehow rather.
Bottom right.
Come on. Somehow it doesn't want to go to full screen. Okay, here we are. Okay, what I would like to report is a observation that we made last week, a fast radio burst, and just let me say just a few words for those who have not come across fast radio bursts in any detail, what these are. These are single pulses which come from deep space, from cosmological distances. And why that is known that they're coming from far away is because of the high dispersion, which means that during the propagation, the lower frequencies get more delayed than the others. And the first of these strange kind of effects was observed by Duncan Lorimer when he looked through archival data. And this is really the first detection. So it's the characteristic behavior. So you have a pulse, and the higher frequencies, in this case 1.5 gigahertz, arrive earlier than the others. So this was a detection. It was a bit questionable in the beginning whether it was really a astronomical event, but there were more observed. And the original thinking was that these are one-time events. They are come from far away, but are relatively bright. So those must be one-time events, something like two neutron stars colliding and things like that. However, Laura Spittler looked through archival data of the Arecibo telescope, and she found a fast radio burst which actually repeated. So it was not a one-time event. It came over and over again, not frequently, but every now and then. And many more of such repeaters have been detected since then. So now we have two categories, fast radio bursts which have only been observed once, and others which have been observed multiple times. It's still unknown whether they're really the same type of astronomical objects. Some of these repeaters have shown that they have an episodic behavior. So there are periods of time when they are more active than others. So that's also something that has been learned over time. Now, there's one repeater called FRB 2020-1124A. That's the date of its discovery, which is a repeater. It was first detected in November last year by the CHIME FRB collaboration. CHIME is this telescope in Canada. It stands for Canadian Hydrogen Intensity Mapping Experiment. And it's very well suited to detect fast radio burst. This particular fast radio burst has a dispersion of 413 parsec per cubic centimeter. So it is clear that this is a cosmological distance, because our own galaxy cannot produce that amount of dispersion. Now, what happened was that end of last month, on the 31st, the CHIME collaboration issued an astronomer's telegram saying, well, we see enhanced activity, so it may be worthwhile by other observatories to observe that. They had at that time reported 6 events. The strongest was on March 23rd. And when you look through their data, in the meantime, they have observed 6 more. And because of this astronomer's telegram, quite a few, let me quickly show the events here. What is shown here is what is called the dynamic spectrum from the CHIME. This is the pulse itself, and then it's shown the occurrence over frequency. The CHIME observes from 400 to 800 megahertz. It's not across all of the spectrum, but 100 megahertz in this case. So there are 6 events. This one is I would say, a bit weak, a bit questionable, but anyway. But that triggered really a number of observations by various telescopes, including ourselves. We got interested in them. So let's quickly look at what happened at other telescopes. There was the Australian ASCAP. They reported that they had observed something on the April 1st, quite a strong one. In this case, 700 to 800 megahertz, 100 megahertz wide again. Fairly strong one. The second one was reported for April 2nd. Then the big Chinese telescope, the 500-meter telescope, they reported that they saw between April 1st and April 6th more than 100 bursts, but they didn't publish any further details yet. So I don't know how strong those were. The Deep Space Network Goldstone antenna, I think that's a 34-meter dish. They observed an S-band and reported a non-detection. The Very Large Array made an observation where they had a 2 gigahertz and 2.4 Jansky times milliseconds pulse. And Effelsberg did a non-detection observation at the higher frequencies. I think in the meantime, they have seen something at a later date. Anyway, we were very excited to do our own observation, although we thought, well, chances are slim, but if you don't look, you don't see anything. So we started right on the 31st of March and observing with our 25-meter dish, looking at our L-band, which is 100 megahertz wide. And we had a couple of very questionable events. I mean, those were the kinds of thing where you look at the signal, say, oh, maybe it's something, but more likely it's wishful thinking. So we didn't quite, we weren't convinced about those results until the 15th of April when we had this one. Now, this is a very strong pulse. You can see it is coming over the full 100 megahertz of our bandwidth. It had exactly the dispersion as expected. We measured 412.8. The nominal is 413. This one has a signal to noise ratio of 85, so it's extremely intense. You can also see that it is not completely uniform across the spectrum. There are sort of enhanced areas and gaps. This is typical scintillation, what you can expect. It's exactly the scintillation that one can expect. But still, you have to be sure. Everything looked right. So we said, let's do a test on how exactly does the dispersion look like. So we checked it against the theoretical curve. This is the arrival time of the pulse, and the red line is the theoretical value at a dispersion of 413. And I should note, it's not so easy to be seen here. It's not a straight line, it's slightly curved. And exactly our signal has exactly the dispersion. So this is very clearly a fast radio burst that we have observed. Looking a bit at the parameters of this fast radio burst, it's relatively narrow. 1.5 millisecond is the full width half maximum. But what is really, really exceptional is the peak flux density of 215 Jansky. This is a very intense fast radio burst. I don't know how that fits into the into the whole scheme. It's probably one of the most intense fast radio bursts that has ever been observed. Few other parameters which we derived from our data. It's the dispersion measure close to 413. The fluence, that is the integrated power over the poles, was 334 Jansky times milliseconds. So this is really, really intense. Same for the 215 peak density and the peak flux density I've already mentioned. This made us very excited, and we wanted to share this excitement. So we issued an astronomer's telegram, like the other observatories have done, giving all the parameters and so on. You can also see the data and the spectrum on our website. So this was a very exciting moment for us to not only be the first amateur telescope to ever observe a fast radio burst, but also to observe one of the most intense fast radio bursts that have ever been observed. So this is what I can report. I should also say that this is not a one-man show. It's many people are involved at our telescope. 90 hours of observations that we did until we had this event. The most time was done by Hans-Peter Löger and Bert Engelstich, who did the telescope operations. I would also like to thank the professional colleagues from the Max Planck Institute to say they told me, yes, this is real. And they also were helping me with Astronomer's Telegram. And of course, the whole AstroPilot team has been behind that. So this is what I can tell at the moment. We are continuing observations, obviously. And as we speak, the telescope is running again to see whether there's any more coming up. And I'm ready to take questions. Thanks.
Clearly, the speed at which you got to sample is generates a lot of data. How much data are we talking, and how and where are you storing all that data?
Well, this data is running about at the resolution that we're running there. 1.5 megabyte per second is the data rate. We typically store it on an SSD for an observation, then transfer it over to our storage systems. I'm not sure how much the data is. It's probably something like 4 terabyte that we have from this specific observations, but we have something like 300 terabyte of storage available at the observatory.
Have you written software to try and detect them, or are you doing it manually?
No, that's done by software that's available from let's say the astronomy community. We are using. It's the main thing is called Presto, which is also used for pulsar observations.
Right.
And then there's some other around that.
But it sort of spots anomalies and things like that. Yeah.
It's essentially what we have to do is we have to record the data. We do an on-the-fly fast Fourier transform of the 100 megahertz of spectrum. This is done in hardware or an FPGA, and that spits out the spectrum, and that gives us the roughly 1.5 megabyte per second.
Good stuff. Okay.
All right. Any other questions?
Thank you very much, Wolfgang. I just think it's fantastic that the amateur community can make such a contribution. We've got a few minutes left. There are some questions. I think what I'll do is send those on, and then I'll send them out once we get answers from Whit. And in the last 10 minutes this evening, we've seen we've had a presentation from somebody with huge amount of expertise and experience, and from Wolfgang also with massive expertise and experience and some fantastic kit. And one of the things I would like us to do on these evenings in the second part is allow folk with less experience to share what they're doing, because we all started somewhere, and for all of us there was a time when we had no experience. And I'm feeling a little bit nervous about this, but I do want to share what I've been doing, particularly as we've been focusing on magnetometry this evening. And that was the first experiment that I started playing around with. So just to encourage those of you that are less experienced or thinking about doing some observations, here goes. I'm going to share my screen. I think it's that one. First of all, Mark Edwards sent me a slide. Can you see that? Can somebody indicate that they can see my screen?
Yep.
Yep. Okay, that's great. So yesterday, Mark Edwards, who gave
one thing, Paul. Could you turn your microphone down a bit? It's clipping really badly.
Oh,
so we're getting a lot of crunch.
Yeah, okay. I tend to speak loudly. Oh, yeah, there's my mic.
Thank you.
Okay, is that better? Can you hear me okay now?
Yeah, less crunchy, definitely.
Yeah, okay, that's fine. Yes, so Mark Edwards sent me this data this morning. Unfortunately, he couldn't be with us today, and I said to him if it was okay, then I would share it with us all this evening. So he took this data yesterday at 24 kilohertz, and it's a beautiful ionospheric disturbance chart with a correlation with the X-ray data from the GEOS satellite. So thank you, Mark, for setting that in. So geomagnetism, it's a beginner's tale. It's where I started. And like Whit, I just love these animations from NASA showing the violence of our sun, and the fact that we as amateurs just playing around in our labs can detect these effects. I think it's just really astounding. So as I said earlier, when I first started thinking about this, came across the manual from Yucara, and in fact Whit's chapter on the theoretical justification for all of this. And I acquired one of these boards that uses a magnetoresistive device, and it's just 2-axis orthogonal. And there's this beautiful image in the manual, because as Whit said, the orientation of the board is absolutely critical. And this picture of the board on the planet just illustrates how to get started with nulling out the sensor to get something out of it. So the hardware side, the magnetometer has an analog output for the X and the Y, and it also has a port for Starbase, but I don't use that. So I just ran the analog directly into an ADC, into a Raspberry Pi, and that was my first experience with trying to get a Raspberry Pi to work and read the data coming off the I2C bus, and writing a bit of Python. The other thing I wanted to do was try and get my head around Visual Basic for the post-processing, which is what I did. So on the software side, as I said, I've got Python running on the Raspberry collecting the data, and I take a reading every second and then average it for a minute on the Raspberry Pi. And then every day using the Windows scheduler, the Excel macro fires up and generates these data files on the left, on the right hand side. So I get a PDF that I send to John Cook. I get a JPEG that I'll come back to in a minute. It saves the XLS. It also saves a JPEG onto the Raspberry Pi, another Raspberry Pi, and I'll come back to that as well. And then, because I had the magnetometer on the roof of my lab, when there were days with a wide temperature change, I did find that it drifted with temperature. So I got the macro to send me an email. The reason I take a JPEG file is that at the end of the month, it's very easy to flash through 30 JPEG images using the multimedia software on Windows. So it means reviewing the data manually. I can quickly spot if there's an event that needs further investigation. So this was an example from last month that John Cook published on the bulletin, and that's quite typical of the data that comes out. I've got a whole load of Zoom messages over my over my slides. I can't see the date. Okay. Once I got some data, it's always I always wanted to be sure that it was like genuine, and so I had a look and found the Swedish Institute of Space Physics have a fantastic database, and you can just dial up a day and they will and you can download the file for that day, and you can see that on this day, the date of which I think it was sometime in January. Maybe you can see the date on it. I can't because of Zoom's overlaid. And then also the British Geological Survey have a good database. And in the future, I wasn't aware of this, I'll have a look at Reeve's data as well. Incidentally, I contacted the British Geological Survey, and head of geomagnetics is quite happy to talk to us at some point. So maybe next year or later this year, we'll see. Now, this was data from just earlier this week, as many of you that look at these things noted that the sun has been quite active. And this again is the comparison between my data on the right-hand side and the IRF data on the left-hand side. And one thing that I want to have a look at, particularly after tonight's talk and looking at this comparison, is have a look at the integration, because I think I'm might be losing some detail because of the of my integration times. Okay, so the end point in my experiment is that I want to bring my geomagnetic data together with VLF observations, my muon counting experiment, eCallisto, which I plan to start in the summer, together with X-ray data from GEOS, and bring it all together to correlate so that I can make solar observations using all these techniques. So that's me. My journey is an absolute. I think that's the last slide. Yeah, journey is an absolute beginner, and thank you for indulging me. And it's just the beginning of a whole lot of I was going to say work, but that's probably the wrong word. Excitement, I think, out here in my lab. I remember Wolfgang once said that, why do we do it? And he answered the question himself by saying, because it's fun. And if it wasn't fun, I wouldn't be playing around out here. So yeah, thank you. If there's any questions, I'll get somebody else to answer them. But we'll see.
Well, hopefully, Paul, by tomorrow, by lunchtime tomorrow, you should have enough ammunition to get on with your project.
I know. Yes. I mean, I did a bit of coding when I was a student, and then picked it up 50 years later. So from Fortran to Python, it's been with nothing
Yeah,
much.
a bit different.
But yeah, very different. So yeah, it's been fun. I'm at the beginning of quite a steep learning curve, and I guess that's true for many of us playing around. So once again, I'd like to say thank you very much to our speakers tonight for being so enlightening and inspiring. I've thoroughly enjoyed this. I'm going to stop the recording, but I'll leave